Hello there. Just a quick example to show taking an implicit derivative. Hopefully I'll make a couple mistakes along the way so you can correct me and help me figure it out. So we've got a polynomial here in x and y. If we take a quick look at the graph, we can see it's a pretty funky thing and it is definitely not a function, right? As you look at the Desmos graph, you can see that I did find the derivative, so that's what I'm going to show you is what does that derivative look like. Jamboard? All right. So when we take the derivative, an implicit derivative, what we're thinking of is if every variable is a function of another function. So we're really extending the chain rule idea. So when I look at a term like this, I think about it as a product. We've got the x squared times the y. And then I'm also going to think about it like somehow the x is a function. And what that's going to make a difference as is when we take the derivative of it, we're going to multiply it by kind of a little dx to show the change of the inside. Okay, so taking the derivative of a product, right, is the derivative of the first times the second, and then the first times the derivative of the second. So the derivative of x is 2x, but like I said, I'm going to think chain rule like and mark it with a little dx to show that that's what we took the derivative of there. And then we take the product derivative of the second part, derivative of y, which is 1, but then we're going to mark it with a dy to show what did we take the derivative of. There's only one variable in this x squared term, only one variable in the y squared term, and here we have another product. So the derivative of x is the 1, but I'm going to put the dx to show I took the derivative of an x there. And same thing, it's 1, the derivative of y, but I'm going to put a dy. Only one term, derivative of y is 1, mark it with the dy, and then the derivative of 10 is 0. 10 is not changing. Okay, so the next step in finding an implicit derivative is to sort out the dx's and the dy's. So I'm going to put all the terms here. So we've got 4xy, that's a dx. We've got minus 2x, that's a dx. We've got a minus 2y, that's a dx. And that's it for the dx's. And then we've got the dy's, the 2x squared, 2y, minus 2x, plus 2. That is a lot of 2's. Okay, so we've got all this is equal to 0. So to find the derivative, dy by dx, we want to separate those out to the different sides. So I'm going to subtract over the dx one. Minus 4xy plus 2x plus 2y, because I subtracted it to the other side, dx. Divide both sides by dx. And we're thinking about it like it's a geometric quantity. So in part, it's manipulation of notation, and in part, we're actually keeping track of kind of physical quantities here, which is why things tend to work out the way we want. But then we also want to divide out by this side. Since every term has a factor of 2, we might want to simplify it, see if it helps us figure out what's going on. But there we've got the derivative. So what do we do with it, right? So dy dx is equal to this complicated function of x and y. We've got it here. Notice I don't have Desmos trying to graph it. It can't graph a function of two variables, right? Because what that does is at every point here, it gives a value for it. But what I could do is say if there was some point that I know what it is, 0, 2.317, I can ask it what is the value at that place. 0, 2.317. It'll tell me about 0.698, so around 7/10, which means that the slope at the y-axis is a little less than 1. That's pretty believable from looking at the graph there. What we are interested in often from these derivatives is where is the numerator equal to 0. That'll tell us where the tangent line is horizontal. Okay, so you notice there's this whole red graph's worth of places where that function of x and y is equal to 0. But the only places that really matter to us is where does it cross our original function. Because we don't care about any x and y. We just care about the x's and y's that are on this function. So here we found one local maximum, which looks like it's probably a global maximum. And here we found local maximum, not too far off from each other, but they're both the solutions of this equation that are on the equation we were thinking about. Now that would change if I change this equation, right? So if I was looking at kind of a different level curve, then that would change what points these were. Okay? And if we wanted to know where is it undefined, are there any vertical tangent lines, right? We'd look for where the denominator is equal to 0. So if we look where the denominator is equal to 0, it looks like it doesn't intersect our graph at all, right? Even if we zoom out, it's a parabola opening with, looks parabola-ish. And in fact, if we look at the equation, we can see it is a literal parabola. But it's a parabola. It doesn't look like it's going to intersect our curve. So there's probably no places where this function, this equation up here, this implicit function, is going to have a vertical tangent line or an undefined slope. And that's the example. So thanks very much. Hope it helps you with this Desmos activity that we're doing for class.